morning, everyone. I'm Miss Barnes, and welcome to Math Mondays. This segment is for kindergarten through second grade. Today, you'll notice that I'm outside here at Luce Park. The Rose Garden is just behind me. Today, we're going for our monthly math walk. Do you remember a couple weeks ago when we went on our August math walk? That was the first math walk we ever did. Do you remember how to do one? So today, while we're here walking at Luce Park, we're going to focus on counting. We're going to count from the number 1. We're going to count on a lot of different numbers. And we're also going to keep track of the total number of objects that we count. You may want something to write with, a marker, pencil, crayon, and a piece of paper in order to keep track of all the things we count. At the end of our segment, this will be very important. Take a second now, and let's get ready to learn. As we get started here, we need to remember how to take a math walk. I told you today that our focus is counting. So, taking a math walk focused on counting just means that you stop in certain places and count the things you see. For example, here right in front of me, I see 1, 2, 3 street lamps. See? I've already practiced my math today. Are you ready to keep going on our walk? Next up, the tennis courts. As we walk along the west side of the park, one of the things we come across are the tennis courts. And you'll see this morning there are actually some people playing tennis. But we're going to talk about these park benches here. So as I get closer, we're going to count them. Are you ready?
Make sure you look closely. One of the park benches is sort of hard to see. Ready? 1, 2, 3, 4, 5. Did you count 5 park benches also? Great job! Let's keep walking.
As we're coming down the hill past the tennis courts, one of the first things I saw was this patch of trees. Can you count the trees that you can see in the foreground?
If you're having trouble deciding which trees to count, we're going to look for the trunks that have light on them. Are you ready? 1, 2, 3, 4, 5, 6. I see 6 tree trunks that have light on them. You may have counted a different number, and that's okay. For the purposes of our lesson, we're going to say that there are 6 trees in the foreground here.
Along the south edge of Luce Park, you'll find a monument to the Battle of Westport, which happened in 1864 during the Civil War. Along this pink gravel trail you'll see are plaques that you can read in order to gain more information about the Battle of Westport. Can you count them?
Let's see if you can find them all. 1, 2, 3, 4, 5, 6, 7, 8, and one more. There it is in the background. 9. There are 9 plaques on the trail that you can read.
As we continue to walk along the south edge of Luce Park, I looked to the left and noticed that I could see the tops of some of the buildings. Can you try to count them? I know they're far away, but I bet you can count at least 4. Let's try.
1, 2, 3, 4, 5. I can see 5 different buildings. It's okay if you came up with a different number. Just remember that at the end, when we talk about what we've counted, I'll be using 5.
We're heading down the trail on the east side of Luce Park towards the pond. We're going to take a moment to pause here, and I'd like to see if you can count the number of objects that are painted black This one might be hard. Make sure you look closely. Are you ready to count them together?
Here we go. 1, 2. I can also see the trash can in the background. That's 3. And right next to it, there's a street lamp. 4. I count 4 objects that are painted.
We finally made it to the pond at Loose Park. Have you been here before? It's a really cool place to walk in the morning because the ducks are super active. So if you look here to the left on the center island in the middle of Loose Park, or the pond rather at Loose Park, you'll see some ducks out there. Do you think we could count the number of ducks we see?
We are going to practice counting the ducks 2 ways. The first way is we're just going to count by ones, like normal. Can we count the ducks by ones? We'll start with the duck that's closest to me, the one that's right by the water. 1, 2, 3, 4, 5, 6. And then do you see those ducks sitting in the shade? 7, 8. There's a duck right beside the tree. 9. I don't know about you, but I see a duck farther to the right, also sitting in the shade, for 10 ducks. It's okay if you counted a different number. But now we're going to practice counting by 2s. Remember, when we count by 2s, we think the odd number and count the even number. Are you ready to practice? We'll think 1, but we'll say 2. Think. Say 4. Think. Say 6. Think. Say 8. Think. Say 10. So skip counting by 2s gets us 2, 4, 6, 8, 10 ducks on the island in the middle of the pond.
While walking along the pond, I noticed that on the very far side was a group of ducks fishing. You can see over here that duck is fishing. You'll see kind of his tail feathers pop up as he goes down and gets a fish, and then his head will pop back up. So we're going to stop here, and I'm going to ask that you count the ducks that you can see here. Remember that one that's super far away? And see if you can add those to the ducks that we counted before.
Let's count the ducks first. 1, 2, 3, 4. Here in this shot, there are 4 ducks swimming in the pond. Now let's think about how to add those. We had 10 ducks in the first group, and 4 ducks in this group. How many is that all together? That's right, 14. 10 plus 4. Before we call it quits today on our math walk, I'd like to review all the places we visited and all the things that we counted. If you'd like to practice your addition skills when we're done here, I challenge you to add together how many things we counted total. We won't go over that today, but we will in the future. For now, let's talk about all the things we counted. We started over by the tennis courts, where we were able to count 5 park benches. When we continued down the path, we came to a grove of trees, where we counted 6 trees. As we continued along the trail and got to the south end of the park, we counted 9 plaques about the Battle of Westport. Then we counted 5 building tops and 4 objects that were painted black. When we got to the pond, we counted the ducks, and we practiced counting by ones and skip counting by twos. The first group of ducks we saw had 10 ducks, and the second group had 4.
Well, friends, that concludes our math walk today, and I'm so glad you came with me. Remember that we practiced our counting skills today. We counted all the things we could see. We practiced counting by twos, we practiced counting by ones, and we practiced adding similar groups of things together. This week, your challenge is to come outside with me, take a math walk, talk to your friends, your parents, your siblings, your grandparents, your aunts, your uncles, whoever you have close to you. Have them help you count. And my challenge to you is to see how high you can count this week. I can't wait to see what you come up with. It's been great having you in class today. I'm Miss Barnes, and I'll see you next week for Math Monday.
Kindergarten is great at Kansas City Public Schools.
I know they have really good teachers. I know this is a great school.
They teach them stuff that I thought my kids would never be able to know at the age of 5.
Since deciding to send our kiddos to a neighborhood school, we've become even more of a part of our community.
Now is the time to enroll your future kindergartner for the new school year. Visit enrollkc.org today.
Good morning. Thanks for joining us for Math Monday. I'm Erin Dorsey, and I'm one of the elementary math coordinators for Kansas City Public Schools. The last few segments, we've been working hard solving word problems in math and using the 8 mathematical practices to help us. Today, we're going to continue those lessons using a tape diagram to solve our problems. A tape diagram is a strategy that can be used to solve any word problem. If it sounds new, it's really not. It's very similar to number bonds, and you use number bonds all the way in kindergarten, 1st and 2nd grade to help you solve problems. A tape diagram is just taking that number bond a little bit further. So let's get into our problem.
Let's take a look at our problem. A Kansas City store has 458 Chief shirts, 212 Royal shirts, and 277 KC hats in their inventory. How many more shirts does the store have than hats? The first thing I want to do is identify the most important information that will help me solve my problem. Do you see any information that we could use? If you're thinking this information here, you would be correct. 458 Chief shirts, 212 Royal shirts, and 277 KC hats. That information is going to help me solve my missing pieces. It's going to help me solve for my missing pieces. Another piece of information that's extremely important is the question, because that tells me what I'm trying to find out. So as I said before, today's strategy is going to be using a tape diagram. Now, you may have heard of this same strategy referred to as a bar diagram. Those are the exact same thing, it just has 2 different names. So if you hear your teacher or someone else say bar diagram or tape diagram, we're talking about the same strategy. With this strategy, we need to figure out what we're comparing, and we can find that in our question to this problem. How many more shirts does the store have than hats? So what are we comparing? If you said shirts and hats, you would be correct. So I'm going to list those 2 things off to the side. I have shirts and I have hats. S for shirts, H for hats. For the shirts, I'm going to draw a bar. This is my total amount of shirts. And I know that this total is made up of 2 parts, and I get those parts from my problem. I have 458 chief shirts, which is 1 part, and I have 212 royal shirts, which is my 2nd part. Together, they give me my total amount of shirts. Now for the hats, I have a total, and that is 277. But if I'm comparing my hats to shirts, that means that my bar for hats needs to be the same size as my bar for shirts. And it's not, is it? I have all of this space here to make up, and that is my unknown. That's what I'm trying to figure out. So the first thing I need to do is figure out what this total is. How do you think I can do that? By adding, exactly. I have 2 parts and now I need to find the total, and I can find the total by adding. So I'm going to add 458 plus 212, and that will give me my total amount of shirts. 8 ones plus 2 ones is 10 ones. Put my placeholder down, carry the 10. 5 tens plus 1 10 is 6 tens, plus another 10 is 7 tens. And then 400s plus 200s is 600s. My total amount of shirts is 670 shirts. So remember, if I want to make my hat bar the same size as my shirt bar, that means my hat bar also needs to equal 670. Do I have a piece of that total? Yes, I do. 277 is a piece of the total. So I have 670 and a piece. To figure out the unknown piece, I can subtract, and the answer will be my missing piece. So I'm going to go ahead and do that. 0 ones minus 7 ones. Right now I don't have enough, so I'm going to have to break down a 10. That means this would be 6 tens. And I'm going to put the 10 here. 10 ones minus 7 ones is 3 ones. Now I have 6 tens minus 7 tens. I don't have enough right now, so I need to break down this 100. If I break down this 100, this becomes 500s. And I put my 100 over here. So I have 160 or 16 tens. 16 tens minus 7 tens is 9 tens. And then 500s minus 200s is 300s. This is my missing piece. So I'm going to put that back up here. So that means 277 plus 393 equals 670. If we did our math right, all of that should equal. Let's check it real quick. 277 plus 393. 7 plus 3 is 10. 7 tens plus 9 tens is 16 tens, plus another 10 is 17 tens. Carry. 200s plus 300s is 500s, plus another 100 is 600s. So 670. Yes, it does equal. We got it correct. So let's make sure we've answered our question. How many more shirts does the store have than hats? Okay, well, if the store has 670 total shirts and it only has 277 hats, this missing piece here is how many more shirts it has than hats, and that is 393. So my answer is 393 more shirts than hats. Let's take a look at another problem. The same store sold 304 Royals jerseys in June. I'm going to highlight that because I know it's important. And 34 fewer in July. That is also going to be important. How many jerseys did the store sell in both months? So I need a total. It's going to be for both months. So when I set up a tape diagram, I know that I'm comparing two things. In this problem, what am I comparing? If you said the months June and July, you would be correct. So I'm going to write those down here. June and July. In June, there were 304 jerseys sold. In July, there were some jerseys sold, but it was 34 jerseys less than 304. So that means this right here is going to tell me how many jerseys were sold in July. What operation do you think I could use to find out how many were sold in July? Subtraction, yes. I have a total of 304 jerseys in June, and I know that I sold 34 less than that in July. So therefore, I can subtract. 304 minus 34. 4 ones minus 4 ones is 0. 0 tens minus 3 tens. I'm going to need to break down 100 to do that. So I'm going to break down 100. That means there's going to be 2 hundreds left here. I'm going to put my 100 down here, which is also equal to 10 tens. 10 tens minus 3 tens is 7 tens. And then 2 hundreds minus no hundreds is 200. So in July, they sold 270 jerseys. Am I done? You're right, I'm not done. Because if I go back to the question, it asks me how many jerseys were sold in both months. How am I going to figure that out? That's right. I am going to add my jerseys in June, which is 304, to my jerseys sold in July, which is 270, and that's going to give my total amount of jerseys sold in both months. So 4 ones plus 0 ones is 4 ones. 0 ones plus 7 ones is 7 ones. Or I'm sorry, I made a mistake. Did you catch it? That's right, I was in the tens column, not the ones column, so let's redo that because mathematicians want to be precise. I have 0 tens plus 7 tens, and that leaves me with 7 tens. 3 hundreds plus 2 hundreds equals 5 hundreds. That gives me a total of 574 jerseys sold in both months.
So what do you think? Bar models, tape diagrams, 2 different names for the same strategy, but it's a strategy that's going to work for you all the time. And it takes your knowledge of number bonds and helps you figure out how to solve word problems that are maybe more complex than what you're used to. The main thing is that you are using what you know in the problem to solve for what you don't know. and that you're using a strategy that allows you to organize your thinking. Now, I'm sure you noticed in the problem I made a mistake. What did I do when I made that mistake? That's right. I stopped and I went back and I corrected my mistake. I didn't just keep going because mathematicians are precise. One of the 8 mathematical practices is to attend to precision, and that is very important. We attend to precision by making sure that our thinking is organized, that our work is not sloppy and all over the place so that we can understand what we're writing, and that we keep using the right type of language, and we keep explaining our thinking as we go along. All of that allows us to attend to precision while using our background knowledge to solve for what we don't know. I hope you enjoyed your time today, and I hope that when you're solving problems with your teacher, that you can use this strategy to help you. Have a great day. See you later.
I love Southeast because of the culture, the band program, and restorative justice.
I love Southeast because of the academics, sports, and students.
I love Southeast because of the people, the energy, and the advanced classes.
It's not alike. I love Southeast because the students here at Southeast are full of potential and they believe in achieving anything. We are Southeast. Southeast. We stand shoulder to shoulder.
Join the Southeast family. Enroll today.
Hello, my name is Mary Jo Fender, and this is Middle School Math. Today we're going to be learning about powers and exponents. How would you write repeated multiplication using exponents? And what if you have a product, how would you write that using a power? You'll need to grab some supplies, paper, pencil, and a good attitude is all you need, and let's get learning. Did you know you've already learned about powers and exponents, especially in science class? Did you know that the earthquakes and the Richter scale are all based on powers of 10? You've probably heard on the news recently, probably in California, about an earthquake that measures a magnitude of 2. Well, to write that mathematically, you would say 10 to the second power. And if you wrote it in repeated multiplication or write it out in expanded form, it would look like 10 times 10. Well, let's say you have a magnitude of 4 for an earthquake. You would write that as a mathematical term as 10 to the 4th power. That would look like 10 times 10 times 10 times 10 as you would write it in repeated multiplication or expanded form. Most of the time what you're going to do with these numbers is you're going to compare them. You're going to compare 10 to the second power to 10 to the first power. How much stronger is it? We'll talk about that in a later lesson. Did you know that your computer storage, which is known as bytes, are also based on powers? They're based on powers of 2. You've probably seen in an advertisement, or you've even looked on a box or even looked up specs for a computer or your iPhone, how much memory or storage it has. Did you know mega means million, and it is written as a power of 2, 2 to the 20th power? That's 20 2's combined repeatedly. That's a lot of 2's, and I really don't want to write that a whole lot. So we're going to shorten that to 2 to the 20th power. If you notice giga means billion. And to write billion as a power of 2, you would write 2 to the 30th power. Again, that's 32, or 32's repeated. And that's a lot of 2's. Again, I wouldn't want to write that out a whole lot of times. Let's talk about vocabulary before we get too far into this lesson. When we talk about a power is the complete term. So if you notice, I just circled the power. This particular power would be read as 5 to the third power. Well, powers also have two particular parts, and those parts have a special function. The first part of a power is going to be your base, and your base is going to be your factor that you're going to be repeating in your multiplication. Your exponent is going to be how many times you repeat that factor. So for a power, for the power we have listed 5 to the third power, we would write that out in expanded form rather, 5 times 5 times 5. Now, when we evaluate, you're going to work left to right, or you can use the associative property and chunk them together in groups of 2 and get your product. So let's take this one step farther. How would I multiply this out to get my product? Well, I would say 5 times 5 is 25, and then times 5, don't forget that, is going to be 125. So remember, vocabulary for powers are base, exponent, and the complete term is called a power. So let's take a look at how you might see it in your math classroom. So we have a table here. We have 3 categories of our table. We have expanded notation, we have power, and then we have value. Most of the time, you might see value written as product. I've seen it both ways, but product is really the mathematical term for value. So I'm going to cross out value and write product just to let you know that is the proper term. Now, your job, if this was in your math lesson, is going to fill in the missing cells. And so if we take a look at our first row, our expanded notation is going to be 3 times 3 times 3. So if you remember, we have our base and we have our exponent. Our base is our factor that we're repeating, we're multiplying repeatedly. So that's going to be 3. And our exponent tells us how many times that factor is repeated. And our 3 is repeated 3 times, so it's 3 times 3. Our next step is our product. And so I'm going to refer back to our expanded form, and I'm going to show my work in that value cell. So my first group is 3 times 3. I know 3 times 3 is 9. My third 3 is going to be multiplied times 9. So 9 times 3 is 27. So my product or my value for 3 to the third power is 27. So let's look at our second row. I've left off expanded notation. I've left off the product. What I've given you is the power. You need to fill in both of the other 2 cells. So I hope you're saying to yourself for expanded notation, well, okay, I have an exponent of 3 that tells me how many times my term or my factor is going to appear. So I'm going to have 3 terms. I'm going to be multiplying those together. So the next thing I'm going to look for is my base. My base is my factor telling me what I'm going to multiply. So that is 6. And so I'm going to fill in those 3 little lines that I left for my number of factors. So my expanded notation for 6 to the third power is 3 times 3 times 3. Again, how would that look for our product? So I'm going to say 6 times 6 is 36. And then I'm going to multiply times 6. Now, sometimes when you get numbers that are too big, you may have to work off to the side. You are required in middle school to know powers up to 500 and something. So I'm going to do some quick multiplication. That's 36. That's 18, 19, 20, 21. So that is going to be 216. So I know my product of 6 to the third power is 216. Well, let's look at our product. We have to turn it around and reverse it. So there's a couple of different ways that I can write 16. I hope you're saying to yourself, oh my gosh, yeah, I know that. What two numbers multiplied together are going to give you 16? Remember, they have to be the same. I hope you realize that it's the number 4. 4 times 4 is 16. That's the fastest way to get there. And our power, remember, our base is 4. Our exponent, because we have 2 4s, is 2. There's another way, but for time's sake, we're just going to stick with that one. So let's take a look at -2 to the third power. Notice this time I have the -2 in parentheses. Those parentheses need to be paid special attention to because they tell you what is the base. In this particular case, the base is going to be -2. Notice my exponent is 3. So that tells me that in expanded notation, my base of -2 is going to be repeated 3 times. Notice I wrote this particular expanded notation in parentheses. I did that so I wouldn't have to lose my negatives. When I stack multiplication in this particular way using parentheses, remember that is multiplication, so you don't have to put a times sign or your dot to represent your multiplication. So the product or the value, so -2 times -2, remember integer rules, negative and a negative make a positive, 2 times 2 make 4, and then I'm going to multiply times my third -2, a positive and a negative making a negative, 4 times 2 is 8. So the product of -2 to the third power is going to be -8. My third example is 10 times 10 times 10. You're right. As a power, that's going to be 10 to the third power. But what would it be when we write it as a product? So remember, 10 times 10 is 100 times 10. That's going to be 1,000. So my product for 10 to the third power is going to be 1,000. Okay, now it's your turn. Go ahead and take a few moments, copy the table. I filled in the rows for you. Well, I filled in one cell of the rows for you. Take a moment and see if you can figure out what goes in the other cells. I'm going to be right here, and in a few minutes, I'm going to come back and I'm going to show you those answers. Okay, so let's take a look. So notice my expanded notation is -5. I have parentheses around that -5, so that tells me that my base is -5. So when I write it as a power, I'm going to have to include that -5 in parentheses. Now, in our next lesson, we'll talk about what does that mean when I leave the parentheses off. It means something totally different. So remember those parentheses, it's very important. So when we come up with our value, we're going to say -5 times -5, that's 25, times my third -5, that's going to be -125 for my value. Remember, another word for value is going to be our product. So how would you have written 7 to the second power in expanded form? Remember, our exponent tells us how many times. We're going to be writing the factor of 7, which is our base. It's 2, so I'm going to say 7 times 7. For our product, 7 times 7 is 49, so that tells me that 7 to the second power, the product is 49. So let's look at 64. What numbers multiplied together equals 64? There's a couple of different combinations, but the one probably most obvious has 2 factors. Big enough hint? I hope you said 8. 8 times 8 is 64, so how would you write 8 times 8 when it's in expanded notation as a power? You're right, it's 8 to the second power. I have 2 8s, that's the 8 is my base, the 2 represents how many times, and that is my exponent. Thank you for joining me today, and remember our goal today was to learn how to write repeated multiplication using exponents, and we worked a little bit about how to turn a product into a power. Thank you for joining me. My name is Mary Jo Fender, and I'll see you next week to continue our discussion on powers and exponents. Remember, keep practicing. The more you practice math, the better you get. Have a great week.
I chose manual because it's challenging and fun, and it can help me with college.
I chose manual because I wanted to get a jump start in my career with culinary arts.
I chose manual to acquire skills I'd use in real life.
I chose manual because I want to be an ER doctor, and being an EMT is my first step.
Kickstart your future today at Manual Career and Technical Center. Manual is open for all 11th and 12th grade students in both Kansas and Missouri. Learn more today at enrollkc.org/manual or call 816-418-5200.
Hello, my name is Marcelina Lirius and welcome to Math Monday. Today we will continue solving one-variable equations. You will need your pen, your notebook, and if you have a calculator, that would be helpful. When you are ready, let's get started. So last week we solved one-step and two-step equations using the bar model and inverse operations. In this lesson, we will solve multi-step equations, and these equations have variables on both sides. Our goal is to find the solution. That is, we're going to find the value of the variable that will make the equation a true statement. First, let us review some of the items that I gave you for practice. Okay, I have here the solution, and I want you to compare your answer and check if you got the correct answer, x is equal to 12. And if you did not, please take note of your errors and make the corrections on your paper. The second item on the practice is to find the solution to the equation 3 times the quantity x plus 4 is equal to 27. Some students would use the distributive property to solve the equation. That's still correct. Okay, so using the bar model, we now have to represent 3 times x plus 4, or stop. Using the bar model, we are going to represent the left side of the equation 3 times the quantity x plus 4 with 1 bar, and the right side 27 with another equal bar, or a rectangle. So we have 3 groups of x plus 4. We can write this as x plus 4, x plus 4, and x plus 4. So that is the representation for that first bar. Then we are going to decompose 27 into 3 parts. you now have 9, 9, and 9. Did you get the same answer here or same entries into the bar? Stop. We are going to decompose 27 into 3 parts. 9, 9, and 9. Then we are to break this down, x plus 4 into x and 4, x and 4, x and 4. Then to decompose 9, we are going to find, if we're going to decompose 9, one of the numbers will be 4 and the other is 5. 4 and 5, 4 and 5. Then we have here x is equal to 5, x is equal to 5, x is equal to 5, and this gives us the solution to the equation. Okay, copy. And on the right side, you see the solution using the inverse operations. And you will arrive at the same value, x equals 5. Now we're ready to solve equations with variables on both sides. So if we have 5y equals 3y plus 8, using the bar model, we represent 5y with one bar, and the right side of the equation with another bar or another rectangle, 3y plus 8. So we are going to decompose 5y into y, 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 and y. And our 3y plus 8 will be y, y, and y, and 8. Okay, so this is our 3y plus 8, and this part here is our 5y. Okay, you can copy notes. Then let's look at this part here. Notice that 8 is represented by 2 y's, so we are going to break down 8 into 2 parts, 4 and 4. Then we have y, 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 and copy the rest of the entries in the bar. Let's look at this part here. Notice that 8 is represented by 2 y's. So we're going to break down 8 into 2 parts, 4 and 4. Now we're ready to solve equations with variables on both sides. So 5y equals 3y plus 8. So using the bar model, we will represent the left side by this bar, and the right side 3y plus 8 by another equal bar or rectangle. We will decompose or break down 5y into y, 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 and y. Then our 3y plus 8, we can write this as y, 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 and 8. Okay, let's look at this part here. Notice that y is represented, notice that 8 is represented by 2 y's or equal to 2 y's. So we can break down 8 into 2 parts, 4 and 4. Then we copy the rest of the entries. So y, 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 and y. Okay. Then our solution to the equation is equal to 4. Y is equal to 4. Okay, I'll pause and give you time to process. So now let's solve this using inverse operations. Now let's solve this using inverse operations. Our goal is to keep the variable on one side, and traditionally, we eliminate the term that has the smaller coefficient. In this case, 3y. So if we subtract 3y from both sides, so if we subtract 3y from both sides, so I now have 3y minus 3y. This left side will be equivalent to 2y, and the right side will be equivalent to 8. So we'll do some shortcuts here. And this is, we are subtracting both sides by 3y. That's still justified by the subtraction property of equality. Then we divide both sides, or find the inverse operation for multiplication. So that is dividing by 2. And this gives us y, or 1y, is equal to 4. So y equals 4 is the solution to this multi-step equation. And we can always check our answer by substituting this value to the original equation. So 5y equals 3y plus 8. So if y is equal to 4, then 5 times 4 must be equal to 3 times 4 plus 8. So 20 equals 12 plus 8, and 20 equals 20. This is a true statement. So let's have another example. 3y plus 4 plus y equals y plus 7. Let us first combine 3y and y, and this is equal to 4y. So our left side is reduced to 4y plus 4. So we represent the first bar with 4y plus 4, and the other bar will be represented by y plus 7. Okay. Are we ready? Now, let's break down or decompose our 4y plus 4 into. Okay, so we have 4 here, and y, this represents 4y plus 4. And the second expression here, y plus 7, so y and 7. Next, so notice that we can decompose 7 into 4 and 3. Okay, so you now have here 7 and 3. And let's copy the rest of the entries here. Let's look at this part of the bars. 3 is represented by 3 y's. So this means we are going to break down or decompose 3 into 3 parts, 1, 1, and 1. Then copy the rest. So we have here, notice that y is equal to 1 here. This is 4. Okay, we can decompose 4y plus 4 into, okay, y, and y. Then we have 4 here. Then write our y plus 7 here. Okay, so we can decompose 7 into 4 and 3. Again, this 7 here is our 4 and 3. Let's copy the rest of the entries, y, and y. Then, take a look at this part here. We now have 3 y's equal to 3. So we decompose 3 into 3 equal parts. So 1, 1, and 1. Then copy the rest of the entries. So y and y. And our solution here, y is equal to 1. So using inverse operations, the first step is to combine like terms. By like terms, we mean they have the same variable and same exponents. In this case, we combine the numerical coefficients of 3y and 1y, which will give us 4y. Then plus 4 equals y plus 7. Then, to isolate the variable here, we'll get rid of y from this side by subtracting y from both sides. Okay, so giving us 3y plus 4 on the left side and 7 on the right side. Again, this is justified by subtraction property of equality. So, to isolate the variable 3y, let's subtract 4 from both sides, giving us 3y, equals 3. And by inverse operations, let's divide by 3, and this will give us now y is equal to 1. This is the solution to the equation, and if we substitute this to the original equation, this will make this equation a true statement. So let's summarize what we did in this lesson. Okay, we solved multi-step equations, and these equations have variables on both sides. We used the bar model and inverse operations, and these two methods actually help us understand better how to solve equations. So I will give you 2 problems for practice, and I hope to see you next week.